Let's continue our exploration of small samples and the student t-distribution by looking at problem 2 on page 346. Here we are asked to find the difference in population means to make some comments about the difference of the means. So let's look and see what it's actually asking us. The problem comes in with three parts. Problem type, first of all, would make a point estimate for the difference of the population means. We have two independent sample means. Remark here that if the samples are not independent, if they are so-called panel sample, where we do the same experiment twice, once before and once after something happens, or with paired people like mother and son, or second cousin, third cousin, or classmates from two different statistics classes, or some pairing like that, why then we use a different technique than shown here. The difference, of course, is that here we use a pooled way of calculating the standard deviation. So look at that in a second. First problem type is point estimate for the data which is given here. Data for all three parts is we have two samples, and each sample has the same number of data points, 10, and sample mean of the first is 600 with a sample standard deviation. Remember, that's we calculate the sum of the squares of the deviations and divide by n-1 before we take the square root rather than dividing by n. And for the second, sample mean is 550 and deviation 15. So let's see how we might go about working that problem. The method, of course, comes from the central limit theorem. Our best and only estimate, it says, is that the best estimate we have of the difference in the means of the two samples is just the difference in the means of the samples themselves. So it would be 600 minus 550, or 50. For part B, we need to find the confidence limit at 95% confidence. So we need to first find the margin of error. The margin of error is a critical value of t depending on alpha over 2, which you remember depends on the confidence level, and the degrees of freedom multiplied by the standard deviation of the population of the difference of the means. And in this particular type of independent sampling, the standard deviation here is equal to the pooled standard deviation times the square root of the sum of the reciprocals of the data set sizes. This gives more weight to the smaller samples, of course. So let's see how that works out here. Our alpha is 1 minus the confidence level, 1 minus 0.95, which is 0.05, but we are spreading this interval on both the right and the left sides of the mean, so the tails each have area alpha over 2, which is 0.025. And in this type of problem, we have two constraints. We have the constraint on the first sample because we specified the mean, and a constraint on the second sample because we specified its mean. So we actually have to worry about calculating n1 plus n2 minus 2. I don't know where I got the 210. It's not supposed to be there. Let's see if we can get rid of it. No, it's not. 20 minus 2 is 18. And then find from table 3, page 406, the critical value of alpha over 2 and 18 degrees of freedom, which is, as I read the table down the 95% confidence limit column to 18 degrees of freedom, I read 2.101 as our critical t-value. Notice in this type of problem, we have yet to need to calculate the actual t-score. We'll do that when we use the hypothesis test. We don't need to do it here. Then we compute the pooled variance. variance of each sample is weighted by the degrees of freedom in that sample divided by the total number of degrees of freedom. So here I have the pooled variance. I weight S1 squared by the ratio of the degrees of freedom in that to the total degrees of freedom. It's n sub 1 minus 1 over n sub 1 plus n sub 2 minus 2. The minus 2 comes because we're adding n sub 1 minus 1 plus n sub 2 minus 1 to rewriting it. And then similarly weight on the variance of S2, pardon me, of sample 2. And because n1 and equals n2 in this particular problem, I can simply factor the 2 out of the denominator, cancel with the numerator, and we get a simple 1/2 times the variances summed, which is 274.5. Now the standard deviation of the distribution of the difference of means is that pooled standard deviation times the 1 over the square root of n1 plus 1 over the square root of n2. Again, because n1 is equal to n2, both are 10. 1 over n plus 1 over n is 2 over n. And that evaluates to 7.4093. So I can then go ahead and calculate the margin as a product of that standard deviation I just calculated times the critical value of t, which I had to use alpha over 2 and df to look up. And that gave me a margin of error of 15.567, almost a straight. Then the lower limit is the mean value minus of the mean difference minus the e, and the high value of the confidence limit is the mean value plus the margin of error. So we get a low value of 34.433 and a high value of 65.567. So we have constructed then a confidence interval estimate of the mean of the population. In part A, we calculated a point estimate. Here, it's a interval estimate. Part C is a claim that the difference between two means is non-zero, statistically significant at the 2% level. So the counterclaim is that the two means are equal at the 2% level. The null hypothesis would be then the claim that has an equality in it, which is mu sub 1 minus mu sub 2 is equal to 0. That is, that the two means are equal. And the research hypothesis is that they are not equal. At least that's what I get from the wording of the problem on page 346. So H1 is our research hypothesis, and it says the difference is not 0. And we're going to test the null hypothesis at the 2% level using a small sample t distribution and calculating a t star, which is our statistical test. It's the difference in the sample means minus difference in population means under the null hypothesis. So the mu sub 1 minus mu sub 2 term up here is 0. And again, the two sample sizes are equal, so I have S sub p times the times the square root of 2 over n, which turns out to be still 7.409, or the t statistic is 6.748. Then I apply a decision rule, which is I reject the null hypothesis at the 2% level because the t I just calculated for 0.01, pardon me, the t I just calculated, t star, is bigger than the t sub 0.0118 that I read from table 3. I had to reread it, by the way, didn't use the earlier one. So, in common parlance, there's not enough evidence to retain the idea that the difference in the sample means is 0 at the 2% level. Now, the p-value is twice the area to the right of t star. And the area to the right of t star is less than 0.01, according to the table. We can't do any better than that if we use the table. It's not extended enough or precise enough to say more than that. But if we use technology, we use a p over 2 is 1, the total probability minus the probability that the sample lies between minus infinity and 6.748, with 18 degrees of freedom. So we can calculate p then is 2.53 times 10 to the minus 6, which is very strong statistical evidence against the null hypothesis.